on. All right, so we're recording now. So we've officially started. So we've already had some people in class talking about mentioning this homework that's due this evening, right? So we have this homework due this evening. It's not long, but some of the problems on there can be challenging, solving these trig equations, all right, because the solutions are complicated, right? Because there are so many solutions. So so I'm going to ask about this homework first if you've got questions on that one. So let me open that, and let's go straight to the question. So Jad, you mentioned 4. All right, so the first 3 questions should be pretty straightforward because those are all just right triangle sorts of questions. So you really only have one answer, I think, to each question. But like on number 4, this one is going to be more difficult, right? Okay, but oh yeah, because it says find all the angles, right, theta, that satisfy this equation. So you're going to get again, because cosine is periodic, right? The function keeps repeating output values, right? You're going to get lots of angles, right, whose cosine is 5/7. Even though they might be hard to track down, there are lots of angles whose cosine is 5/7, and so we have to type in all those solutions. So that's the complicated part of the problem, right? Okay. And what makes this one a little bit worse is the fact that you can sort of immediately realize, right, that, oh, theta is not going to be a special angle, correct, right? Our solutions to this problem, there are lots of answers for theta here, but the solutions theta to this problem are not going to be special angles, right? Because there's not any special angle, right, whose cosine is 5/7, right? So so we're going to be dealing with having to use the calculator here, right? On this problem to figure out what our candidates there for theta are going to be, right? Okay, so I'm gonna so for you guys at home, also be thinking about other problems that you might be having here from this homework. But this particular problem is going to be is a really good example because it's going to encapsulate, I think, all of the difficulties that you have in solving trig equations, except possibly for if the equations get slightly more complex. There are some other examples at the end that you might think of as being more difficult, but this one certainly is sort of a basic trig equation to solve. So let me lower the screen here and let me see if I can find some paper to write on. I mean, some virtual paper here to write on. So let me find my notes and see if I've got any blank space in my notes or if I'm going to have to add some paper here. I think, let me see, I've got a recall practice for you guys. So, but I think I've got enough room there for that recall practice. So let's try writing here. And all right, so your problem is slightly different, right, Jad, but it's going to be essentially the same. So you can follow these steps, right? So cosine theta is equal to 5/7. Remember, you really don't have to write the parentheses around the theta there. You can just also write this equation as cosine theta equal 5/7 without the parentheses, means the same thing, right? Okay, so the key step here, right, is you have to free the theta. This is the way I think of it. That was the name of a movie, wasn't it? Oh no, that was Free Willy, wasn't it? So, but anyway, we're going to free theta, right? Okay, from the cosine. That was supposed to be a joke, which y'all aren't laughing. All right, so y'all never saw that movie. Okay, so we have to free the theta here, right, from the cosine. And so, how do you do that? So, how do you undo that cosine, so to speak? Yeah, you apply the inverse function, right? Okay, so we do that process a lot in solving equations. We just don't think of it initially when we're solving equations as applying an inverse function, but that's really the process that we use in many instances to solve many sorts of equations. So we're going to apply the inverse function, right? Which you can write down as cosine to the -1. You can write down arc cosine as well here instead of cosine to the -1 of cosine theta is equal to, and be sure you do that to both sides, right? So cosine inverse of 5/7, and here we should get just theta, right, on the left-hand side. These two functions should cancel each other, so we just get theta, and then we have to figure out what the cosine inverse of 5/7 is, okay? And since this is not a special angle, as I mentioned, we know theta is not a special angle, right? We're gonna have to rely on our calculator. So you're gonna have to punch 5/7 into your calculator, right? And then apply cosine inverse on your calculator to that, and get a decimal approximation here. What does your calculator say? Let's put it in radians though. 0.775. What are the instructions in the problem? Maybe I don't need it in radians. Oh, it does say degrees. Oh, okay. So sorry about that. Oh yeah. Yeah, angles between 0 and 180 degrees. So I think that's right. Okay. And then round your answer to one decimal place. Oh, so they're not asking for all solutions here. They're just asking for the solution between 0 and 180 degrees. Okay. So, but let's write down all solutions anyway, just for fun here, so that we can practice that. Okay. Remember, when you apply cosine inverse, right, to a number, remember the range of cosine inverse, correct, is between 0 and pi, right? Okay, so you are going to get an angle when you apply on your calculator. When you apply cosine inverse to 5/7, you're going to get, because your calculator knows the correct range for cosine inverse, you're going to get an angle between 0 and pi, between 0 and 180 degrees. Okay, and so Iris keeps telling me it's what, 44.7 or something. 44.4. All right, so round it to one decimal place per their instructions. So I think that's really just the only answer we have to get. Oh, Jed, were you trying to type in more answers or? Oh, yeah, the full list of solutions. Okay, so yeah, that's just a problem with the instructions there. So that's just another reminder to read instructions there very carefully in WebAssign, right? So they only wanted one solution between 0 and 180 degrees. So once you've got the 44.4 here, you're done. So it really was kind of an easy problem, but we're gonna find the other solutions as well. Yeah, Amanda. Yeah, really? Okay. Even with the 5/7. Oh, all right. So, oh, okay. Well, let's try this one then and see. Let me try it and see what happens. So, you know, WebAssign is programmed wrong sometimes. So, so 0, find all angles. Oh, let's be careful now. Find all angles from 0 to 180 degrees. So is there another one? Let's draw a picture of this then, right? Okay. So let's draw a picture to make sure we're not oversimplifying the problem either. So let's see. So 44.4 degrees, right? It's going to be right about there. You know, that's almost 45 degrees, right? So there's 44.4 degrees. Okay. And the other solutions then to this problem, right, are going to be 44.4 degrees plus multiples of 2 pi, right? Okay. Correct. But then you also, if you wanted to find all the solutions to the equation, you would want to find another angle from 0 to 2 pi, from 0 to 360 degrees, whose cosine is 5/7. All right. That cannot be in the second quadrant, however, because why not? But that's right, because cosine is negative in the second quadrant. So from 0 to 180 degrees, which is the first and the second quadrant, that's the only one. So I think that is the only, because they said find the solution from 0 to 180 degrees. That's it, right? Okay. If we're punching in this numbers right on the calculator, let me check it. Because y'all claim to be getting the same numbers. So yeah, that's 44.4. Okay. So we've got that right. Where is the other angle from 0 to 360 degrees then? Right? If it's not in the second quadrant, right? Can't be in the third. So it's got to be what? Yeah, over here in the fourth, right? Okay. So if you look for the angle in the fourth quadrant, whose reference angle is 44.4 degrees, what angle is that going to be? So if we draw a picture of it, it's going to look something like this, right? Because its reference angle, remember, reference angles are always positive. So its reference angle is 44.4 degrees, but the angle that we would be looking for is this large angle, right? Okay, whose reference angle is 44.4 degrees. What angle is that going to? What now? 315.6. Sounds right. So there's the other angle from 0 to 360 degrees, right? Whose cosine is 5/7. So if you're going to write down all the solutions to the problem, right, you would take the 44.4. I'm writing in degrees now, and then add on multiples of 2 pi. 2 pi in degrees, of course, is 360 degrees. So you would add a multiple of 2 pi to this, or take the 315.6 also and add on multiples of 2 pi. When I was doing this in the notes, I was adding and subtracting multiples of 2 pi, but in WebAssign, you're entering the answers, just write plus k times 2 pi. Okay, so there are all the possible solutions to this equation, all of them. Okay, all right, of which we only wanted the one from 0 to 180, which is apparently supposed to be 44.4. So let me try entering that in and see what we've done wrong. I may have to look for. I can look at the answers, but that will take me a little while. Am I supposed to put degrees on it? Is that what we're missing?
Yeah.
Oh, you do have to put degrees.
Yeah.
I know sometimes other times.
Oh, you got it right. Oh, okay. That's right. Okay. Yeah, Emil, you need to speak up so we're not all here scratching our heads there. Okay. All right. So how do I find degrees on here, Emil? Where is that? Is that a symbol? Is that a symbol?
Yeah. Yes.
Oh, right there? Oh, okay. Okay.
Yeah. And other times too.
All right. Finally, let's submit this. I thought I saw a check mark there. Yeah, I did. Okay, so there it is. All right. Okay, so just that one small thing there, right? So y'all are not going crazy. You know what you're doing. It's 44.4. All right. Well. Okay. So let's look at the more complicated version of this. Is that number 8? I was thinking number 9. So this was also giving you difficulty, Chad, or you were just doing something stupid? Okay, well, yeah, because they're almost identical, right? So let's try 9. 9's going to be a little bit harder, but only because you know in 8, right, that you're going to get special angles here, right? Because square root of 3/2 is that's a cosine value for a special angle, right? So this one we really don't need a calculator to help us with. But here, of course, no special angles, cosine is 0.08. So we're going to need the calculator here. So let's try this one. And I think in this case, we really do need to use radians. All right, so that's going to make it just that much harder. All right, because we're going to have to think in radians here for a little bit. They've already told us it's all right. So, okay. All right, well, let's go back to the notes. So, so you know how to do this now. So y'all can sort of guide me here. I think we can almost use exactly what we've got written here, right? Already. So I want cosine of theta is equal to, in my version of the problem, it was 0.08. All right, so this tiny little fraction here, 0.08. So we already know, right, that we're going to apply the arc cosine or cosine inverse to both sides of the equation. And that's easily done on the left-hand side, right? So we just get theta. And now also easily done on the right-hand side as well, because this is going to require the calculator. So, make sure you're in radian mode. So what is cosine inverse of, if I can get this into radian mode. Of 0.08. I get 1.49. Is that to 2 decimal places? Did it ask for 2 decimal places in the problem? I think it did. Oh, okay. All right. So 1.49 in radians. So let's draw a picture of that, because we've got to put down all the solutions. Oh, by the way, now our solution list we can already start, correct? Because we know it's going to include 1.49 plus multiples of 2 pi, right? So that's 1/2 of your long list of solutions there. But to get the other half of solutions, remember, you have to find the other angle from 0 to 2 pi, right? The other angle from 0 to 2 pi, whose cosine is 0.08. Its reference angle is going to be 1.49 radians. Here's where things get tricky, Sonny, because we have to draw a picture of this, and it's hard to draw a picture in radians. So let's see if we can do that, though. So what does 1.49 radians look like to start with? Well, here's where it may help to cheat and take the 1.49 radians and convert that to degrees. Okay, just to help you draw the picture correctly. It's important you draw the picture correctly, I think. All right. It doesn't have to be super accurate, but you know you want to get your angle in the right quadrant. What is that, Sonny? Just multiply by 180 and divide by pi, right? Yeah, that's probably about right. So 85.37. So it's, almost vertical, right? That angle is almost vertical, but not quite. It's almost 90 degrees, right? So it's almost vertical. So here is 1.49 in radians. Okay. So the other angle from 0 to 2 pi, right? It's got to have 1.49 as its reference angle, but we've got to get it in the right quadrant. But this cosine is positive, so we have to be in the quadrant, the other quadrant where cosine is positive, which is what, Iris? Yeah. 4, right, exactly. So I want the angle in quadrant 4, whose reference angle is 1.49. So when you draw that, Iris, it's going to look like this. Right, okay. It's actually kind of be this angle kind of rotated around the x-axis, because you want the reference angle to be 1.49 in the 4th quadrant. So now we have to figure out what the full angle is, right? So if we loop around here and draw an angle whose reference angle, draw an angle in the 4th quadrant whose reference angle is 1.49, what's that going to be? Well, to calculate that, right, remember 1 full revolution is 2 pi, but you're going to subtract off this reference angle of 1.49, right? So the angle that we're looking at here is 2 pi minus 1.49. And we want to write that down to a couple of decimal places, right? So How much is that? 4.79. Does anybody agree with that? 4.79. Okay, yeah, if we're off by one decimal place, web assignment will probably stab us in the back, right? So we have to be careful. All right, so there it is. 4.79 plus multiples of 2 pi. So I think that's the solution. Does that make sense now, Jack? Okay.
So we're going to enter. Just like-
Yes, it doesn't it ask for a comma separated list?
We all do, that's all.
Yeah, comma separated list. Right, so the first one, the 1.49 plus k times 2 pi, comma, and then the second one, whatever that was, plus k times 2 pi. Yeah. Not working? Did you try it? No, I think you type k with the keyboard, don't you? Let's try typing it. Just a regular k? Oh, okay. Let me try it here and see if I can type this in without screwing it up. So it was what, 1.49 plus, where's my plus here? Plus, is that going? Plus k. Oh, that comes in right. Oh, but now, how do you, do you have to use the palette to get the times? Oh, in front of the k? Oh, yeah, that would be the easy way to do it, I guess. But now I do have to get the pi, so that's on the palette, right? Well, does it know pi? It knows pi? Oh, so it speaks Greek, so that's nice. All right. So plus 2 pi times k like this.
Oh, there we go.
And then comma, and then I forgot what the other one is. 4.79. Same thing, right? Where's that plus? Plus 2 pi k. Hooray! See how smart we are? So there we go. Now, since we're looking at it, what are you going to do in 12? To start the problem?
10.
Yeah, we have to get tan by itself. So, and here you have tangent squared. Be nice if that were just tan to the first part, because you could just move the 1 over and divide by 3, right? But this is tan squared. So what's plan B here, Amanda, for isolating that tangent of theta? Let's write this down. So let me squeeze it in over here. I'm not going to go through the full problem. But we have 3 tangent squared theta minus 1 equals 0. So any suggestions? I had a different idea. Okay. If this were, think of tangent as just a single item, right? So, and first replace it just by x. Just call it x, just to make this look easier to you. So if you had 3x squared minus 1 equals 0, how would you go about solving that one? Yeah, Emil, one approach might be to factor, but unfortunately, you can't factor 3x squared minus 1. All right. There you go. Right there. Yeah. Normally, factoring would be your best approach, but 3x squared minus 1 doesn't factor. If that were, by the way, if that were x squared minus 1, that would factor. How does x squared minus 1 factor? That's difference of 2 squares. This is a perfect square. This is also a perfect square. Do you remember how to factor difference of 2 squares? Yeah, it's x plus 1, x minus 1. So this would factor, but the 3 screws it up. 3 is not a perfect square. So this is not difference of 2 squares any longer. If it were 4x squared, that would also be difference of 2 squares. But the 3 messes it up. So that's unfortunate. But Amanda says that's okay because she has another idea anyway, which was what?
Just here. That's
Yeah, you could add 1 to both sides, right? So you get 3x squared equal 1. Then divide both sides by 3. And you have x squared is equal to 1/3. And now you can very clearly see, right? Oh, if x squared is equal to 1/3, that means x has to be the square root of 1/3, right? Okay. But don't forget, you have 2 possible square roots of 1/3. So write them both down. So you have plus or minus the square root of 1/3. Okay. Well, you're going to use the same idea here, except with tangent. So if you solve this equation, like we solved this algebraic equation, you end up with not x, but tangent of theta is equal to plus or minus the square root of 1/3. And the square root of 1/3 is plus or minus 1 over square root of 3. So you have to think about, what angle has tangent plus or minus 1 over the square root of 3? Start with the positive one first. You know one? I think that's a special angle. You have your chart? What? 30? Okay. So pi over 6. All right. So so one possibility here is pi over 6. That would be an angle whose tangent is positive 1 over the square root of 3. And then to get the rest of the solutions, remember for tangent, then you don't have to worry about finding a second solution. You just would take the pi over 6 plus multiples of pi. Okay, so there's one list of solutions. However, we have one other, we forgot the other possibility here. Tangent of theta could be minus 1 over the square root of 3, right? Minus 1 over the square root of 3. So, minus 1 over the square root of 3. So where is tangent negative?
Oh, you don't have negative x plus
Oh,
yeah,
oh, is that right? No, I don't think so. I think we have another. What does it ask for? But we have other solutions. Does it ask for all the solutions?
yeah. So I don't know, but I'm gonna answer plus potentially.
Oh, well, okay. Well, I'm thinking there's another set of solutions here, okay? Because tangent minus 1 over the square root of 3, that would be, so let's draw a picture again. So we have solutions here, pi over 6, right? Plus multiples of pi plus pi over 6, okay? But for minus 1 over the square root of 3, there are also angles whose tangent is minus 1 over the square root of 3, right? Their reference angle is also going to be pi over 6. You've just got to get in the right quadrant, correct? Where tangent is negative. Where is tangent negative? Quadrant 2, that's correct, right? And also quadrant 4. But we're not going to, I think, look here in, yeah, I don't, well, I guess, yeah, we can look in, can we look in quadrant 2? I'm curious about this one now. All right, okay. All right. So, all right, so all we need is we need one angle, right? From to finish solving here. The other possibility is tangent of theta is minus 1 over square root of 3. Okay. So we need an angle from 0 to pi whose tangent, from 0 to pi whose tangent is minus 1 over the square root of 3. So that is in the second quadrant. That's this angle here in the second quadrant. If I can draw it. Whose reference angle is pi over 6. So what angle is that? The second quadrant whose reference angle is pi over 6. Yeah, 5 pi over 6, right? Oh, that's right. So, so we do have a second set of solutions, 5 pi over 6 plus multiples of pi. When you're solving, remember, when you're solving a tangent equals some number, right? You want to find a solution from 0 to pi, and then just add on multiples of pi. So to solve tangent of theta equal minus 1 over square root of 3, right? You need a solution from 0 to pi. So that would be 5 pi over 6, as y'all told me. And then just add on multiples of pi. What was confusing me is the following. I was thinking, in the fourth quadrant, there's a solution. If you look at the angle minus pi over 6, that's in the fourth quadrant. And its tangent will be minus 1 over the square root of 3. Okay, because the reference angle for minus pi over 6 is positive pi over 6. That solution is included in this list, because if you take 5 pi over 6 and subtract off 1 pi, if k is 1, so if you take 5 pi over 6 and subtract off 1 pi, you get minus pi over 6. So that solution is included in that list of solutions. I was worried about losing that solution and where it went to. It's there. So have it. It's not possible for tangent to have two solutions, but we had two equations here, right, Emil? One of them was a tangent of theta is 1 over positive 1 over the square root, and the other possibility is tangent of theta is minus 1 over square root. So we solved two different solutions. We solved two different equations because we had that square in the original equation, and here are the solutions to the two different equations. Okay, I'm not going to type that in and check it, so y'all can try that. Oh, well, another thing that's on the homework here I see is the last few problems, or the last couple of problems there, involve law of cosines. All right, so that's one of our recall practices for today. We are a little bit behind in our recall practices, so I've got a couple of recall practices. So let's do that then, and that will help you with those last two homework problems to remind you about the law of cosines. Okay. All right, so let me move this slightly out of the way here so y'all can see the recall practice. All right, so this is for everyone to try. This is just the simplest application, I think, possible of law of cosines. All right, so there you have been drawn at the top. The bottom there is just a reminder of the law of cosines. So there you have a triangle that's drawn, right? So it's got a couple of sides. One of them has length 10.5. One of them has length 18. And the angle between those is 40 degrees. And you want to find the length of that side A in that picture. So what's the other length in that triangle? All right, using the law of cosines. Okay, so here, remember, there are three versions of the law of cosines, because you can find the lengths of all the sides of a triangle, or you can find the size of all angles in a triangle using the law of cosines. So there are the three versions of the law of cosines applied to that triangle. All right, so see if you can translate that bottom triangle onto that top triangle, and then figure out which version of the law of cosines you want to use, right? Okay, to solve for that side A. All right. So I'm going to go around and help you with this. And then you've got some little arithmetic, so you will need a calculator to help you with the arithmetic. Okay, so it looks like. Okay. Square here. So right.
But are you looking up? Oh, in that.
Okay, yeah, that's fine.
Okay,
You know
gotcha.
what, 40. That looks like. That's not coming up. Make sure you're. Sure. What's that? Yeah, see, this is a little bit hard to. Okay. I did that really well. Well, this is the simplest application of law of cosines. Ravi, are you saying it's 17.5? Change your mind? I think yeah, I think both of those are wrong, unfortunately, Robbie. Let's see what we got. All right. There we go. Giselle. I think Giselle's answer is closer to being correct. All right. Okay, so let's see. Let's try putting stuff in here, right? I think this is the version, right, of the law of cosines we want to use, right? Because in this picture, we know B, right, is 10.5 and the C is 18. Remember, the way of law of cosines works is you need the angle between these two sides, right? And then you can find the length of the opposite side of that angle. So we do know the angle between the 10.5 and the 18, it's 40. So so angle A here is going to be 40 in this picture. That's the angle opposite little a, right? The side that we're looking at. So we just have to fill in these values. We get a squared is equal to 10.5 squared plus 18 squared minus 2 times the 10.5 times the 18, and then times the cosine of 40 degrees. So you need to have your calculator help you with cosine of 40 degrees, right? Because that's not a special angle, and make sure you're in degree mode. Because a cosine of 40 radians, who knows what 40 radians is, right? That's like 6 revolutions or something. Make sure you're in degree mode there. Anyway, and then ultimately you'll come out with a squared is equal to, what is it, 144 point something? Point, shall I write that down? Point what? 0.6 about. And then when you take the square root, you'll get approximately 12 point what? 12.03, what Giselle got. Okay. Great. Now, in the homework now, you remember you can also use law of cosines to find sizes of angles, right? To find sizes of angles. In that case, you'll need to know the lengths of all of the sides, and then you can use one version of the law of cosines, right, to find the size of the angle. Okay. Ultimately, you will have to use at some point inverse cosine. Okay. In the process. So we can use law of cosines 2 ways, right? To find lengths of sides, but also to find size of angles. So one of those problems in the homework probably will ask you to find the size of an angle rather than size of the length of a side. Okay. Well, so much for the homework. Are there other questions there from so yeah, I think that last problem is a problem that we just mentioned. There you've got the lengths of the three sides. Well, since we're all right, since we're looking at this, let's go ahead and work on this a little bit. So your homework will be slightly different, right? So they're telling us, okay, you've got this triangle, and here are the lengths of the three sides, and you want to find this angle theta, which they've labeled as C. Okay, write these down for me. 13, 9, and 18. I can probably remember that, but let me go back to my picture in the notes, and let's fill in this this triangle. They told us what A was 13, right? And what was it? B is 9, and C is 18. So see, we know the lengths of the three sides here, not one of the angles, but we know the lengths of the three sides, and we want to find this angle C. Okay, that's what you're asked for. The angle opposite side C, which is length 18. All right, so which version here of the law of cosines then do you want to apply? The third one, right? Because that's the one that involves the cosine of angle C, right? Okay. It's easy to remember, though. You really don't have to memorize all different versions, right, of the law of cosines. Since you're looking for angle C, remember you're going to be filling in, right, the sums of the squares of the other two sides, right, minus the twice the product of those other two sides, right, times cosine of angle C is equal to the side opposite angle C squared. So that is 18 squared is equal to 13 squared, right? 13 squared plus 9 squared minus 2 times 9 times 13 times the cosine of angle C. And now this equation, you want to solve it for cosine of angle C, right? So what's 18 squared? 324 is equal to 13 squared is 169. Is that right? Minus, plus 81, 9 squared, minus 2 times 9 times 13. So that looks like, what's 18 times 13? Is that 234? Yeah. Times the cosine of the angle C. So we have 324 is equal to 169 plus 81, which is what, 250? Don't let me mess up this arithmetic, right? Minus 234 times the cosine of the angle C. Subtract 250 from both sides. I don't like that, though. What have I done wrong here? Oh, maybe nothing. All right, so subtract 250 from both sides, so we get 74 is minus 234 times the cosine of the angle C. And now divide both sides by 234, right? So we get the cosine of the angle C is minus 74 over 234, whatever value that is. And now how do we finish solving for C? Yeah, do inverse cosine, right? So apply the inverse cosine. So now your calculator is going to come in really handy because you want the inverse cosine of minus 74 over 234. The reason I was hesitating a moment ago, I thought I had done something wrong, is I was thinking, oh, I'm going to be having this negative value, so I want an angle whose cosine is negative. That means it's got to be in the second quadrant, but I forgot angle C might be bigger than 90 degrees, so it might be in the second quadrant. Okay, this picture is not drawn to scale, right? That was just an arbitrary picture drawn there, all right? So what do you get? 108.4? So there we go. C is approximately 108.4 degrees. I think in the homework it wants more decimal places than that, however.
I just wanted.
Oh, just one is enough? Yay, all right. So what'd you say there? 108.4. If that's right. 108.4. Here they were, yeah, 108.4. Here they were kind enough to put the degrees into the answer for us. So we don't have to worry about that. Let's see if we got that right. Yay, I'm on a streak here. So got that one too. All right. So there's our, that was our recall practice. All right, well, I think y'all are well equipped now to finish this homework tonight. Okay, let's go back to the notes because I got another recall practice for you. So let's see if we can do this one before we have to take our break. This is not on solving trig equations with inverses, but this is solving equations with inverses, but a different inverse function. We're going to ultimately want to solve this equation for x, right? And that means we have to get x from out of this exponent. And to do that, we'll also apply an inverse function. But what inverse function do we use in this situation? So see here you have e raised to a power. That's called the a natural exponential function, right? What is the inverse of the natural exponential function, as we learned? The natural log function, right? So that inverse is what we're going to use ultimately here in this problem, but let's read the setup of the problem. So I think I was making this up at some point last semester, right in the middle. So the number of viral particles circulating in the blood per milliliter of an infected patient given by this function. It's like a complicated function, but that is a good function to model this sort of situation. I'll show you a graph of this function where x is the elapsed number of days after beginning treatment. And we want to know how long does it take for the number of particles to fall to 20, because probably in this problem, if the number of virus particles falls below 20, that cannot be detected, okay? So by standard tests. So probably that patient is considered to be cured at that point, all right? Even though they might still have some virus in their body, but for all practical purposes, they're well. Here's a picture of this. Here's a picture of this function. So remember, this is graphing the number of viral particles after the patient begins treatment. So at first, right, the treatment is working very slowly, correct? But ultimately, the treatment begins to work. And then notice at that point, it may take a while for the amount of medicine in the blood to build up to a sufficient level, kill the virus. But from that point on, notice the virus begins to drop very rapidly. So probably the way these antiviral medications often work is they interfere with virus's reproduction. So at some point, the virus cannot reproduce. And at that point, then your natural immune system then starts clearing the virus. So notice the viral particles drop very rapidly. Okay. And we're interested to when they get down to 20. So that's right here. So it looks like that's what? After 20, a little over 26 days, something like this. Okay, so in about a month, right? This patient is going to go undetectable. And that's our treatment goal. So let's see how long that takes. It looks graphically it's going to be a little bit more than 26 days, right? But let's see how really long it is without the graph. So how do you set up this problem? See, we want the number of particles to fall to 20. Yeah, 20 for y, right? Because in the equation, y is the virus particles, correct? So you just put 20 in for y, and that leaves you with an equation to solve, right? Or x, which is number of days. So that looks like a terrible equation. And we certainly cannot solve this completely using just algebraic methods. So we're going to have to use some of our more powerful methods, but we've already mentioned, right, that's going to involve applying the natural log function. But before we apply the natural log function, we've got to massage this equation into the right form, correct? Okay. Probably what you're saying is right, Amanda, but what's the more correct way of thinking of this? I want to get rid of the fraction. Yeah, multiply both sides by this denominator, right? Okay. You can also think of that as cross multiplying, because that's really what we're doing here. So multiply both sides by this big ugly denominator. So you really haven't gotten rid of the denominator. It's still going to be hanging around, right? Okay, but it won't be in the bottom of a fraction. I didn't leave myself enough room there. Let me move things over a little bit, because I've got to multiply both sides, right, by that denominator. So I also have to multiply the left-hand side by the denominator, 1 plus 9e to the power. So exactly what we wanted to happen happens on the right-hand side, right? The denominator cancels. And now let's distribute the 20 on the left-hand side. On the right-hand side, we just get left with 50, right? So 20 times 1 is 20. That's not bad. And then 20 times the 9e, well, 20 times 9 is 180. So you have 180 e to the 0.5 x minus 30. Okay. So I'm getting there, but because before I can apply the natural log, I need to have just e to the power equal something. So I've got to move the 20, right? And I also have to get rid of the 180. So, well, how do I move the 20? Yeah, just subtract 20 from both sides. So that's easy. Subtract 20 from both sides. And so when you do that, of course, the 20 is going to disappear, right? And on the right-hand side, you're just going to get 30. So you have 180 times e to the power, right, is equal to 30. And now how do you get rid of the 180? Yeah, divide by 180, right? Don't subtract the 180, right? But divide by 180. So divide both sides here by 180. And see, now you're in great shape. So you have e to the 0.5 x minus 30 is equal to 30 over 180, which I guess is better known as 1/6, right? 30 over 180 reduces to 1/6. And now you have the equation in the form that you want it, because you can apply the correct inverse, right, to this exponential function. to get to eliminate exponential function, and that will free the x from the exponent. So as Amanda told us, that that's natural log. All right, so can y'all take it from there? I'm going to watch. All right, now you're going to apply the natural log to both sides, okay, and then finish solving for x. Try to write down first the solution in exact form, and then we'll worry about getting a decimal approximation for what that number is, what that solution is, exact form, right? Hopefully, our decimal approximation will come out to be something like 26 point something. That's what we saw on the graph. Yeah.
Okay, so it's the same.
Yeah, it's the same thing, right? Oh, is this what you got for another? Yeah, that's what we were expecting, right?
No, I,
Has to be natural log. Well, you just want a decimal approximation. Should finish. That's a fraction. Oh, this is right. 5.5. Yeah. Yes. Okay. Next, I think add. Oh, all right. Everyone's almost there. If you're not quite there, you're on the way. So let's finish here. So to eliminate the e, right? To eliminate this exponential function, this natural exponential function from the left-hand side, we apply the inverse of the natural exponential function, which is the natural log function, right? So we take the natural log of both sides. And that magically just cancels those things, right? That's really powerful, right? So that's where inverse really comes in handy. And you just get 0.5 times x minus 30 equal to natural log of 1/6. You can leave this as natural log of 1/6, but by the way, natural log of 1/6 is, just as a reminder here, natural log of 6 is the natural log of 1 minus the natural log of 6. Because remember, natural log of a quotient is the same as difference of the natural logs. But what is the natural log of 1? To answer that question, you need to think of what power of e gives you 1. What power of e gives you 1? 0. So this is 0 minus the natural log of 6. Well, the 0, you can just drop it. So this is really minus the natural log of 6. So you could write that instead of natural log of 1/6. It's negative natural log of 6. All right. Well, never mind. You could still simplify with just natural log of 1/6. So how do we continue solving for x from here? Well, there's a couple of ways you can proceed, but what I was showing people is instead of distributing the 0.5 times the x and the 0.5 times the minus 30, you can do that. That's fine. But you could also remember that multiplying by 0.5, right? I can eliminate the 0.5 by multiplying by 2, because 2 times 0.5 is 1. So there's another way of getting rid of the 0.5 other than distributing it. Just multiply both sides by 2 right here, okay? And then the 0.5 goes away quickly. By the way, these are inverse operations again, right? Multiplying by 0.5 is the same as dividing by 2. You can eliminate that by multiplying by 2. So we get x minus 30 is equal to 2 times the natural log of 1/6. And now just add 30 to both sides, right? So you get x is 30 plus 2 times the natural log of 1/6. And now just estimate that with your calculator. So you might have, your answer might have been written down slightly different, okay, than this. And this does come out to be what is it, 26.4 approximately? So it does coincide with what we saw on the graph, right? See on the graph, to get down to a virus level of 20, right? Go from 20 across, come down, and see that's going to be a little bit bigger than 26. There's 26 on the graph, so a little bit bigger than 26, right? Turns out to be exactly 26.4. There's one like this in the exponential homework. So remember this example when you're working on that problem, maybe the last problem in the exponential and logarithm equation homework, okay? All right, let's stop there. So we'll take a break here. So I'm going to pause the tape. Did y'all get that? Did y'all solve that properly at home? No one answered. Y'all passed out from doing that? There's one on the homework like this, so you got to revive yourself. Let's resume. Every once in a while throughout the course, right, in solving equations, we've been required to remember, right, that we can often factor to solve equations, but that really that ability to solve equations using factoring depends on our factoring skills, correct? And we're getting ready to soup up our factoring skills some. So you probably learned how to factor when you were in, first semester or second semester algebra course, and probably haven't practiced it. You practice it sporadically since then in solving equations, but you probably thought your knowledge of factoring was pretty complete, but it's not, because we're getting ready to learn more about factoring. To do that, we're going to learn more about factoring in the context of studying about what are known as polynomial functions. So we've been talking for several weeks, right, about trigonometric functions, and then not such a long period, right, about exponential and logarithmic functions. Last time we introduced this new category of functions called polynomial functions, but the polynomial functions really are not new to you, because functions that we've been using, some of the functions that we've been using since the beginning of the course are really polynomial functions. We're just going to expand our definition of polynomial functions, or to include a bigger category of functions, and that's what we started doing last time. So remember, polynomial functions are simple in one sense. Their formulas are formed in a very simple fashion, but that doesn't mean that the formulas you ultimately arrive at with polynomial functions are simple. It just means the processes that you use to create those formulas are pretty simple. So the way you create the formula for a polynomial function is you just add on powers of x. They have to be natural number powers of x. By natural number, I mean the powers of x have to be 0, 1, 2, 3, 4. Those are the actually those are the whole numbers. 0, 1, 2, 3, 4. So whole number powers of x. When you combine those in a formula, you get what's called the polynomial function. So here's an example of a polynomial function. Actually, we looked at this example at the end of class very quickly last time. So this would be a very typical example of a polynomial function, because notice all the terms in this formula for this function, right? They're just whole number powers of x. And again, by whole numbers, I mean 0, 1, 2, 3, 4, right? Okay. No negative powers of x, no fractional powers of x. So see, just powers of x added together. Of course, the coefficients on the power of x can be negative, right? Okay. But the powers of x themselves cannot be negative. And so if you form a formula for a function in that fashion, you get what's called a polynomial function, right? So those are very easy formulas to create, just whole number powers of x. Now, of course, if you add enough of these whole number powers of x, right, you're going to get altogether a complicated formula. But the way the formula is built, it's not complicated. Now, polynomial functions play a really important role in calculus and in algebra too. All right, so they play an important role in all of mathematics for exactly that reason. Okay, they have formulas that are easy to create, right? Trig functions are also important functions in calculus as well. We've just spent several weeks studying them, right? But you know, trig functions are difficult to evaluate because they don't have nice formulas, right? Okay, and exponential functions are also can be difficult to evaluate sometimes, okay, because of the nature of their formulas. But polynomial functions have, again, just very simple operations in their formulas, so that gives them kind of an advantage sometimes over trig functions or exponential functions or other types of functions that we study. All right. Okay. Now, polynomial functions, there are lots of different polynomial functions, right? Because it's easy to create these formulas. But polynomial functions do have some features in common. And so I'm going to show you here today what the key common features are for all polynomial functions. But before we do that, though, I need to introduce a little bit of terminology here. Right. So if you have a polynomial function, then the highest power of x, the highest power of the input variable in that formula, remember, the way you create formulas for polynomial function is just adding powers of x, right? So the highest power of x in your formula, that's going to be called the degree of the polynomial function. And that turns out to be really important in helping you understand the nature of the polynomial function, is knowing its degree. So for this polynomial function, right, which again, as I said, was just a very typical example of a polynomial function, it has degree 4 because its highest power of x here is 4. Usually when you write down the formula for a polynomial function, okay, you'll write it in descending powers of x. So normally you would have written x to the first power, x to the 4th power first, right? And then the next highest power, x next, and then so on and so forth. But I mixed up the terms in this formula just to throw you off there. Okay. The coefficient of that highest power term, that's called the leading coefficient. So for this term, x to the 4th power, its coefficient is invisible. So that's understood to be 1, right? So the leading coefficient here is 1. The number that's added at the end of your formula, the constant that's added at the end of the formula, that's called the constant coefficient for your polynomial. So in this case, that is 0.2. Notice that you can also think of this term as being a power of x, because you can write in x to the 0th power here as multiplied times that 0.2. Of course, what is x to the 0th power? How does that simplify? When you raise a quantity to the 0th power, you get what? 1, right? Okay, so you really have here 0.2 times 1, which is still 0.2, right? But my point is, you can think also of that constant 0.2 as being a power of x, because remember I said for polynomial functions, you always form their formulas by adding together powers of x. Well, 0.2 really is a power of x. X to the 0th power, 0 is a whole number. Okay, the whole numbers are 0, 1, 2, 3, 4, etc. Right? So that's a whole number power of x. So it still meets the criteria for a polynomial function. What you cannot have in a polynomial function, in the formula for a polynomial function, as I mentioned, is you can't have negative powers of x. So this function is a perfectly nice function, perfectly simple function, but that is not a polynomial function. Because 1 over x is what power of x? Yeah, that's x to the -1 power. But that is -1 is not a whole number. Whole numbers do not include negative integers. So that doesn't count as a polynomial. Here also is a perfectly nice function and useful function, but also not a polynomial function, because square root of x is what power of x? That's 1/2 power. And remember, in polynomial function, you can only have whole number powers of x. So polynomial functions include a lot of functions, but they don't include 1 over x or x to the 1/2 power. That does not count as a polynomial function. So all the things we learn about polynomial functions do not apply to these two functions, okay? The facts we're going to learn about polynomial functions only apply to polynomial functions. So one way you can recognize the formula for a polynomial function, or one easy way, remember, you cannot have roots of the variable in a polynomial function. So if you see a formula that has cube root of x in it or square root of x in it, that's not a polynomial function. I mean, it may be a perfectly useful function, just not a polynomial. Or if you see x in denominator, like here, not going to be a polynomial function, right? You can't have x in denominators in polynomial functions. You can have numbers in denominators, but you can't have x in polynomial function. Of course, you cannot have trigonometric functions in a polynomial function formula either, right? Okay, or not have e to x in a polynomial function. All right, now, what are the key properties of polynomials then that I keep referring to that all polynomials have in common, right? Well, there's lots of them, but the ones that you really need to concentrate are the following. When you graph a polynomial function, always get a smooth, unbroken curve, right? Smooth, unbroken curve. So it doesn't have any sharp turning points on it, okay? It's always smooth, unbroken, right? So it doesn't have any breaks in it or any holes in it. For polynomial functions, unless there's some other restriction, the domains of polynomial functions are all real numbers. So polynomial functions have domain all real numbers, unless for some reason there's a restriction on the domain, but that has to be given as a special condition. Normally, for polynomial functions, domain is going to be all real numbers, and the graph will be a smooth, unbroken curve. Now, that doesn't mean it's not a complicated curve. It may have lots of wiggles in it, right? But it's not going to have any breaks or holes or any sharp turning points. Doesn't have any corner points on it, okay? Always smooth. Now, polynomial functions may have lots of wiggles. So polynomial functions may switch from increasing to decreasing or vice versa lots of times, but it's not as bad as sine and cosine, right? Sine and cosine have infinitely many peaks and valleys. Polynomial functions do not have infinite many turning points on them, okay? In fact, you can count easily what the maximum number of turning points a polynomial function has. It's always 1 less than 3, okay? So this is a very famous fact from algebra, all right? Actually from calculus. For polynomial functions, the number of turning points is always 1 less than 3. So if you graph the maximum number of turning points is 1 less than 3. It may not have that many turning points when you actually graph it, but that's the most it can have. So if you graph this polynomial function, before you even make the graph, and I guarantee you it's going to be a wiggly graph, you know at most how many turning points can it have? 3, 1 less than the degree, okay? So that's the answer to this question, D here, all right? The maximum number of extrema here, local or local maxima or minima, is only 3. And even better, the maximum number of x-intercepts. So the most number of times it can cross the x-axis is the degree. So whatever the degree is, that tells you the maximum number of x-intercepts you can have. So for this polynomial function, how many times can that cross the x-axis? 4 times, right? Now, it may not cross 4 times, but you know beforehand that's the most it can cross is 4 times. So you don't get infinitely many places where it switches from increasing to decreasing, or you don't get many places where it's going to cross the x-axis, like on the sine or the cosine function, right? That's always controlled by the degree. Let's actually make a graph of this one. I've got a graph of this one already made up somewhere. So let's look at that. And of course, it's going to conform to what I just told you, but let's just check that to see if that's true. Let me see. So I've already graphed this one somewhere here. I think that's this example. Is that formula? Yeah, I think it is, right? Let me scoot this over. So you see you have some wiggles there, right? Okay. But how many turning points did we end up with? 3. Yeah, okay. That was the maximum number. So you have a turning point right here, here, and here. Okay. And that's the most we could have had, right? So you know, actually, even though the domain of this graph is all real numbers, so this graph continues indefinitely to the right and indefinitely to the left, you're looking at kind of the only interesting part of this graph, okay? Because you cannot have any more turning points over here on the right, and you cannot have any more turning points over here on the left, right? All the turning points are there. And how many x-intercepts could it have had? 4? How many x-intercepts do we actually end up with here? Only 2, right? Okay, right. The maximum number was 4, right? But we only ended up with 2. Actually, how could we adjust this formula to get? Could we get 4 x-intercepts out of this? Yeah, how? What would I do there? That constant. What do I need to do to the graph to get more x-intercepts? Well, I need to pull the graph down, right? So I need to shift it down, but you know how to shift it down, right? Okay, by adding or subtracting a constant, right? In this case, I want to move it down, so we could subtract 1 maybe or something, right, from it. Let's see what would happen there if we subtract 1. That pulls it down a little bit. Oh, that's too much. Okay, right? Because I still only had, I have 2 x-intercepts. Let's try 0.5. Okay, oh, that's not quite enough, right? Oh, that's still too much. Let's try 0.4. Does that do it? Just about, right? Okay. Let's try 0.3. Ah, there we go. All right. So by shifting it down by 0.3 units, there we get 1, 2, 3. There's the 4 x-intercepts. Oh, Desmos is really good at estimating. So there's one at 2.024. There's another one. There's one. There's that one. Minus 1.95. Well, our goal in this section is to not have to estimate those x-intercepts with Desmos, but see if we can find those x-intercepts pencil and paper analytic. All right. So how can we find those x-intercepts for that polynomial function? Let's see. When we subtracted 0.3, of course, then you can subtract that from this constant, so you end up with the polynomial. Same polynomial, right? Minus 3x cubed plus x to the 4th plus 2x squared, except the constant changes to what? Minus 0.1, right? Okay. Same, almost exactly the same polynomial, except it does have 4 x-intercepts now, right? Of course, if you change that constant, you could also end up with no x-intercepts. If you shifted this thing up, you could end up with no x-intercepts at all. That's possible too, okay? In the picture. Now, in calculus,
you're going to be concerned with not finding the x-intercepts here. We're going to find those in this class. That's kind of an algebraic problem. The calculus problem would be finding the turning points. So you can see there are 3 turning points here, right? And Desmos does a really good job of estimating for us. I wonder how Desmos knows that, where those turning points are. Well, you're going to learn how to figure out where those turning points are. Calculus, okay? Exactly where those turning points located. All right, believe it or not, and here's kind of the miracle of calculus, that really turns out to be this exactly the same problem as finding the x-intercepts. It's really the same problem, okay? All right. So let's go back to the notes there. Now, I want to remind you that, again, we've already been talking about polynomial functions since the start of the course. So because familiar functions to us, as I mentioned last time, are polynomial functions. So linear functions, which we know look like this in general, right? Y equals mx plus b. Linear functions are polynomial functions, right? Okay, because how do you form the formula for linear functions? You just have powers of x. What power of x? Well, what power of x is this? M times x is what power of x? What power of x is that? What's the exponent there? 1, sure, right, okay. That's x to the first power. And this constant b, of course, which you know is the y-intercept, what power of x is that? You don't see an x there, so 0, right, yeah, so you can think of that as being x to the 0th power, right, okay. You don't need to think of it that way, but you can, all right, that is a power of x. So, see, linear functions are polynomial functions of what degree? 1, right, okay. So linear functions have degree 1. Actually, this is also a linear function as well. Okay, that's a constant function. So you can write this as b times x to the 0th power. What's its degree?
1.
No, what's the highest power of x here, Amanda? 0, right, okay. So polynomials can have degree 0. Yeah, if you just have in your formula, it's kind of a boring formula. If you just have y equal to a constant, when you graph that, by the way, Amanda, what's the picture look like if you have y equal to a constant? Yeah, what is a constant? When you graph a constant function, what picture do you get? You get a horizontal line. Yeah, you do get a line. So this does count as a linear function, but it's kind of a boring function, right? You just get a horizontal line. The y-intercept is b, okay? So you just get a horizontal line that crosses the y-axis at b. So degree 0, degree 1, those are linear polynomials, okay? Those are linear polynomials. There's one little catch. I hate to throw this in because, you know, there's always a catch, right? Y equals 0, that is a constant function. When you graph y equals 0, what picture do you get? That's the x-axis, right? Yeah, y equals 0 is the x-axis, which is a horizontal line, okay? So this is a linear function. That is the only polynomial, however, that does not have a degree. So y equals 0, we consider that to not have a degree, right? Does not have a degree. So that does not have degree 0, okay? But any other constant has degree 0. Still going to give you a horizontal line. And then, of course, lines, when you graph them, you get lines, right? They have degree 1. So degree 1, degree 0, or this one special case that doesn't have a degree, those are linear functions. By the way, does that match our conditions that we just said? Let's see. So degree 1 degree 1, how many turning points could that have? This is degree 1. How many turning points could that have? None. It's 1 less than the degree, Amanda. Yeah. But do lines have turning points? No. Yeah. Okay. So lines don't have turning points. Yeah, Jen. Oh, the sign-in sheet. Yeah. Somewhere here. All right. Before I give you the sign-in sheet, Jed, you have to answer a question. How many X-intercepts can this have? Linear.
Oh,
1, right? Because the degree is 1. But how many times can a line cross the x-axis? Only once, right? It's a straight line, right? It's only going to cross the x-axis once. If it crosses twice, it has a bend in it, right? Okay, but straight lines would not have bends in them, right? Okay, so this has only 1 x-intercept. Degree 0 has no x-intercepts. Okay, degree 0 has no x-intercepts. That's right, right? When you grab a horizontal line, not going to cross the x-axis unless it is the x-axis. This is the x-axis, but remember that does not have a degree. Okay, so we have a little catch there. Y equals 0 does not have a degree. Okay, so if you have this type of formula, ax squared plus bx plus c, that also is a polynomial function. What degree? What's the degree here? What? 2, yeah, because the highest power of x is 2. So if you graph a function like this, ax squared plus bx plus c, by the way, that's called a quadratic function, right? Okay, then how many turning points can it have? 1. That's why we get a graph that looks like this. When you graph ax squared plus bx plus c, you always get one of these U-shaped curves with 1 turning point on it. How many x-intercepts can it have? 2, right? Okay, 2 x-intercepts. Isn't that right? How do you find the x-intercepts of a function? You set it to what? So you would be solving 0 equal ax squared plus bx plus c. How many solutions? You already know how many solutions you're going to get there. How many do you get at most? 2. You find them by what? What are you factoring or quadratic formula, right? Okay, so you can factor to find the x-intercepts, or you can use the quadratic formula. But remember, the quadratic formula only gives you 2 solutions, right? Okay, so polynomials of degree 2, 1 turning point, 2 at most 2 x-intercepts. Of course, if you shift the graph up or down, which would just change the constant, may not get any x-intercepts, right? Don't have to have any. So again, what we're really looking for here is finding the x-intercepts. Let me pass out the roll sheet there. Okay, I'm going to introduce just a little bit of extra terminology here, but it's a very little bit. In the context of polynomials, x-intercepts are sometimes also called zeros of the polynomial. And I don't like that terminology, but that's the way it is. Okay, so x-intercepts often called zeros of the polynomial or roots of the polynomial. I like that terminology better. Okay. I don't like the term 0 because I think that somehow gets confused with y-intercept, but I can't do anything about it, right? Okay, so that's the terminology that's sometimes used. So if someone says, oh, I want to know what the 0 of a function is, or the 0 of a polynomial is, they just mean x-intercept. If they ask what the root of a polynomial is, or the root of a function is, they also mean x-intercept. Now, here's what we know about polynomial functions. So these statements are all equivalent. The first, the 1, 2, and 4 are kind of boring. It's the third one that's the interesting one to us. Okay, so these statements are equivalent. If you say something is a 0 of a polynomial, that means it's x-intercept or it's the root of a polynomial. Then you know, how did you find that 0? You took the polynomial and you set it to what? And solved, right? So you know that number is a solution to this equation. You can find the zeros are x-intercepts of a polynomial. The way you find the zeros are x-intercepts of any function, you set the function to 0 and solve, right? Okay. So if you have an x-intercept of a polynomial, then it's a solution to setting the formula to 0 and solve it. Okay. That's what 4 says. X-intercept is the same as a 0 or root. Okay. However, for polynomials, here's the special thing. That means that this expression x minus c has to be a factor of the polynomial. That's not true of other functions, okay? But it is true of polynomials. So what this third line tells you is you can find roots of polynomials, zeros of polynomials, by factoring. Okay, that's what the third line says, right? Actually, it says you can always find them by factoring. That's kind of interesting, but don't read too much into that statement, okay? You can always find them by factoring doesn't mean that as humans we can carry out the factoring. It just means it's possible to find them by factoring, but it may not be possible for us to find them by factoring. Our factoring skills may not be sufficient to do the factorization correctly, but we are going to learn how to do it better. All right, so let's practice just a little bit with factoring, but this is factoring that you already know how to do. Okay, so let's look at this polynomial, x cubed minus 2x squared minus 4x plus 8. All right, there's a polynomial function. We know it's a polynomial function because in the formula, all you have are what? Powers of x, right? You just have powers of x added or subtracted from one another, so you know that's a polynomial function. So all the things that are true of polynomial functions are true of this function. So what do we know are true of polynomial functions? When you graph it, what's the graph going to look like? A smooth, unbroken curve. Okay. Yeah, the graphs, by the way, Jack, can be all different sorts of shapes. Right. The most you can say is they're smooth, unbroken curves, unless it was a linear function. All right, then you would know more, right? Okay, but this is not linear because the degree is what? 3, right? So this has degree 3. Now, that does tell us something extra about the graph, though. How many turning points can it have? 2, yeah. So it can only have 2 peaks or valleys in it. That's it. How many x-intercepts can it have? 3. So we want to, yeah, because that's the degree 3, right? So we want to find the x-intercepts. Here's the graph, by the way. So see, it matches exactly what we said, right? It's nice, smooth, unbroken curve. The domain is all real numbers, so this graph really extends all the way to the right and all the way to the left. Okay, you just can only see this part of the graph in this picture, but that's really the only interesting part of the graph because you can only have 2 turning points, and I see the 2 turning points. So there aren't any more turning points on the right or on the left. So the right here of the graph is kind of boring, and the left over here will be kind of boring too. This is really where all the action is, around the turning points. And do we see the x-intercepts? I think so. There's 1 and there's 1, right? That's only 2, but 2 is okay. At most, how many could we have? 3, right? Okay, but it looks like we only ended up with 2. And it looks like they are right there at -2 and right there at 2. Okay, so I think the answer to this question, when it says find the zeros, I think the zeros are 2 and -2. But let's see if we can verify that without using the graph. So let's see if we could have found those zeros without looking at the graph. And my only hope here is to be able to do what? So what is this line here telling you? To find those x-intercepts, you're going to have to be able to do what? Factor right. Okay. Now, look, of course, for linear polynomials, to find the x-intercepts, you don't really need to factor, right? You know how to solve linear equations just using algebraic techniques, so you can avoid the factoring. For quadratic polynomials, that's polynomials of degree 2. The factoring might be an option, But if you cannot do the factoring, you can rely on what? What's your other option for finding the zeros? Quadratic formula, right? Okay, so you do have the quadratic formula if you have degree 2. All right. Now, but what happens here when we get up to degree 3? Well, this was a question that was vexing mathematicians for a long time. All right. So they were wondering, if I can't do the factoring here, if I cannot do the factoring here, then what options do I have for solving this equation to find the x-intercepts? That equation would be set this to 0, right? So set the formula to 0. So the question is, the quadratic formula was known since antiquity, since before written history. The quadratic formula was known. All right. So, but for a long time, then mathematicians were wondering, or people who were interested in solving equations like this, were wondering, is there a cubic formula? If I have degree 3, can I find the x-intercepts? And that wasn't, there is a cubic formula. It was discovered in the 1200s, 1100s and 1200s, right at the beginning of the, slightly before the Renaissance, okay? In the high Middle Ages, when universities were first being developed, okay, in Italy, all right, the cubic formula was discovered. It was a great controversy because it was arrived at sort of independently by 2 different mathematicians, and they there was a huge debate about who really had the who really found it first. Okay, now the reason we don't teach you the cubic formula is it's very clumsy to use. Okay, so it's so difficult to use that it's not worth the trouble. All right, so we don't even bother to learn it. Okay, so I've used it maybe 2 or 3 times just as kind of a curiosity, but it's very difficult to apply. Okay, so that's why it was so hard to discover, because it's really not an easy formula, but there is a cubic formula. So you really don't need to factor to solve this equation to find these x-intercepts. Well, then, of course, the question is, what about for higher degrees? There is a quartic formula. I've never even seen it written down. Quartic means 4th degree, or like 4, right? Okay, so 4th degree polynomials are called quartic polynomials. 3rd degree are called cubic polynomials. There is a quartic formula, and so that was that's been known for a while. And so then after that was discovered, of course, the question is, what about for 5th degree? Is there a quintic formula? And the answer is no. All right, so that's really an astonishing thing. All right, you actually cannot write down a formula for higher than degree 4 solving polynomials. So you're really stuck with factoring. There is no quintic formula. Okay, and that was discovered in not until the early 1800s. Right, so I'll see we're sort of on our own here, right? We really need to be able to factor to solve these to find the x-intercepts of these polynomials if we're going to do it with pencil and paper. Okay, all right, so let's see if we can factor x cubed minus 2x squared minus 4x plus 8. We don't often factor 3rd degree expressions like this one. So how can I do this? All right, there's a trick here. And if you weren't shown the trick, you probably wouldn't see this. So again, here's the equation that I want to solve because I'm trying to find the x-intercepts here. What I'm going to do is I'm going to group some of the terms together in this formula. So I'm going to group the x cubed minus 2x squared together, and then I'm also going to group the 4x and the 8 together here. All right, behind this minus sign. Now, when you insert the parentheses, you have to be careful with that minus sign, because to clear the parentheses, you would have to multiply the minus sign through the parentheses, right? And that would give you minus times 4x, which is minus 4x. That's correct. But then what sign do you put here on the 8? To make sure that when you multiply back through, you get positive 8, because you don't want to change the original equation, right? So what sign would go here? Minus, right? So you have to be careful about that. So it's not always, you can just freely insert parentheses into expressions. You have to be careful sometimes. Now, why did I do that? Well, here's why. Look, if you just look at the first set of parentheses, ignore the second set, these two terms you can factor. What can you factor out of x cubed minus 2x squared? Yeah, you can factor out x squared. So you get x squared times x minus 2. Does that multiply back through, right? X squared times x is x cubed. X squared times minus 2 is minus 2x squared, right? Now, from the second set of parentheses, you can do the same thing. What can you factor out from the second set of parentheses? 4. Now, normally that wouldn't be too exciting because this is not factored yet. Okay, this is not factored. By the way, how do you know that we've done some partial factoring, but how do you know the whole left-hand side of this equation is not considered factored? Something is factored when it's written completely as a product. That's what factoring means. You're going to take an expression, you're going to write it completely as a product. But this is not completely written as a product because of this minus sign. See, here you're subtracting to form the expression. You're not just multiplying to form the expression. So this is not completely factored. By the way, that's your rule of thumb for factoring. If you have a plus or minus outside of parentheses in an expression, it's not factored. Okay. All right. So this is not factored, but believe it or not, I'm in better shape because look at these two terms. Here's the first term minus the second term. What do you have common in these two terms? Yeah, the parentheses, right? The x minus 2. So you can factor out now again, x minus 2. Now, when you factor x minus 2 from this first term, you're left with x squared. And when you factor from the second term, you will get left with the minus 4, right? Oh, this now is factored because that expression is formed as a product. The first parentheses times the second parentheses. So you see, we factored it. We're able to factor it. And actually, we can factor it a little bit more because x squared minus 4 is difference of two squares. Remember we were talking about difference of two squares earlier? Emil, how does this factor x squared minus 4? That's difference of two squares. So how can you see these are perfect squares, right? X squared is a perfect square and 4 is a perfect square. How do you factor difference of two perfect squares? You take the sum of the square roots times the difference of the square roots. That's how you always factor difference, not sum, but difference of two perfect squares. Take the sum of the two square roots times the difference of the two square roots. The square root of x squared is x, and the square root of 4 versus 2. So there you've got it. There you have it completely factored. So what are the solutions to this equation now? You have this big product equals 0. That means what? One of the factors is 0. So x minus 2 is 0, or x plus 2 is 0, or x minus 2 is 0 again. I don't have to write that twice. X minus 2 is 0. So what are my two solutions here? Plus or minus 2. There you get it. X is either 2 or minus 2, exactly as we saw in the picture, right? Okay. So there are the two x-intercepts. We found that by factoring. But that was kind of tricky factoring, right? Why was that necessary? Because this is third degree, this is cubic. Okay. All right. If this term were missing, you would have second degree. And if I said, find the solutions to this equation or find the x-intercepts of this function, if you couldn't factor, you wouldn't be all that disturbed, because what would your plan B be? you could use the quadratic formula, okay? But we don't know the cubic formula, although it exists. You know, mysteriously it exists. Then we're only left with, our only choice there is factoring. All right, so I've got one for you, okay? So here is a fourth degree polynomial, because the highest power of x is 4. What's the leading coefficient here? -2, right? By the way you label the leading coefficient, if you don't want to write the words leading coefficient, put a and then write a subscript of the degree, which is 4, right? For the highest power. That's the way of indicating coefficients. If you don't want to write down the words leading coefficient. If you want to write down the constant coefficient, you can write the words constant coefficient, but you can also write a with a subscript of 0, because constant is 0, is x to the 0th power. What's the constant coefficient here? That's a trick question. Is there any constant here? No, because all these terms involve x, right? So there is no constant, so the constant is 0. Well, these things are not really useful to us here in this problem. We want to find the zeros or the roots or the x-intercepts. So that means we have to take the formula and set it to 0 and solve. So this is fourth degree. By the way, that's called a quartic polynomial, quartic. And so our only option here is maybe factoring. Oh, I hope we can factor this one. By the way, I think I have a graph of this one. So let's look at the graph and see if I have the graph. This one? No. That one? No, no, I guess I don't have a graph. Sorry. Ooh, so you're really on your own here. Okay, not even any graph to look at. Maybe be reassured. How many solutions, by the way, can this equation have? So how many zeros can we have here? 4, right? Okay, so we may end up with 4 solutions. All right, so but our only option, since we don't know the quartic formula, one does exist, but we don't know it, is to try to factor. Any suggestions on how to start factoring that? X squared, right? Notice you have powers of x in every term, so you can factor out x squared. I suggest factoring out minus x squared, because that's going to help you in the long run. So if you factor out minus x squared, what will you get left with? 2, positive 2, right? X what? Squared. What you get left with here? Plus x. And then here, what? Minus 3, right? Minus 3. Which means already what's one root? What's 0? Yeah, we know from this factor that we're going to have 0 as a solution, but we may have others, and we can find the others by doing what? Factoring this. Yeah. Okay. Let's try factoring the 2x squared plus x minus 3. If that will factor. See if y'all can make that factor. By factoring that. That doesn't factor, by the way. We're not setting our work, but, yeah, the factor. So. Right, no. Yeah. Now you go. Sign. Contact. Okay. Now have a record. Try. Sure. Okay. So, factor. Mhm. That's good. See.
I have it.
No one. That'll be.
That's choice. I don't know, I was just trying.
I was gonna say that. Factor. Still working on it. Almost. Okay. Yeah, I see that. But in the middle. Minus 3x, but minus x. How can we put that six? Signs, yes. Signs. What is it? There you go. That's right. So factor this. You get 2x3. It's 3. But I want to get it. Alright, so one. So one somewhere is the question gonna be in the right spot. That's it. That's sign. Minus 3. Try it. Experiment, right? So you get it right.
And
So that 3. It's a. Zero. Yeah. Zero. Right. Right. Alright, so. Yeah, so.
oh, this is
No. So.
And you see. Okay, whoops, we have run out of time. All right, so
let's stop there. And we'll finish factoring this one next time, okay? As kind of our reminder of what we were doing. Sorry, guys at home, if y'all got that factored. We'll finish factoring it does factor. So you can solve this, you can find the roots of this polynomial by factoring. All right, let me stop the recording. We got a lot more of this to go. But as we often do, right? We're going to learn some shortcuts, okay? Right. So we're not doing trial and error all the time. That gets a little bit tedious, right?